And welcome back, everyone. We have our next talk right now by Yaakov, which is called Making Swiss Cheese of Ticket Sales. And as we were just talking before in the green room, clearly the abstract has done its job because lots of people are interested in this talk, including me. So without further ado, Yaakov, take it away.
Thank you. Hello everyone, and Shana Tov, Happy New Year, and special hello to our live chat today. I'm Yaakov, and in my day job, I'm a senior software developer at WiseTech Global, where we build software that acts as the operating system for global logistics. At other times, I swap the shipping containers for Docker containers and act as the systems administrator for Smash, the Sydney manga and anime show, where we host an annual convention for all things anime and manga, at least in years where there isn't an active pandemic. Like most conventions, we sell tickets to the event. If you want to get in, you need to buy a ticket. A ticket gets you a badge, and a badge gets you in the door. We sell tickets in two ways, at the door on the day of the event, or online beforehand at a slight discount. And this year, online sales were quite a bit harder than it might sound. We've done this many times before in years past. On our current software stack, we've done it twice. In 2019, we sold tickets, redeemed tickets, and had a whole convention as usual. In 2020, we sold tickets, and we then had to postpone the convention. But our launch of ticket sales did go off without a hitch. This year, for our 2021 flagship event, we opened ticket pre-sales at 10 a.m. on Sunday, the 2nd of May, 2021. That morning, well, it started for me pretty much like any other. I got up, I got dressed, I did the morning prayers, perhaps I should have prayed a little bit harder that everything here would go to plan, and then I logged onto Slack and onto our ticketing website just to keep an eye on things and to watch the ticket sales start to roll in. As the clock ticked over to 10 a.m, I refreshed the page, expecting to see our list of tickets for sale go from nothing to our 3 regular online items, plus the early bird special that was available at the time. Instead, all I got was a loading spinner, and reports started coming in that it wasn't just me. 2 minutes later, the main Smash WordPress website was down too. By 10 past, we were in full battle stations mode, trying to figure out what on earth was bringing our websites down. Some users even reported seeing SQL-related errors on the front end, and that's usually never a good sign. 40 minutes later, at 10:50 a.m, we thought we had identified the problem and deployed a mitigation. But that didn't help. Eventually, at 11:40 a.m, we decided to pull the plug, having only managed to sell one single ticket in our first 100 minutes. Over the next 20 minutes, we discovered that our panic button didn't quite work in the current circumstances, and we had to manually push out a new build of the website with that panic mode hard-coded to on. And yet somehow, ticket sales started flowing through from that point onwards. We spent the rest of the afternoon identifying inconsistencies in the data from those sales, such as users who had paid, but whose payment hadn't been recorded in the system, or users who'd been double or triple charged. In fact, one order had been charged 12 times over, the poor fellow. We added missing links in the data and issued appropriate refunds, and I went to bed that night very confused. So what on earth went wrong here? Before we get to that, let's set the scene. Smash has been running for over 10 years. I first found out about it in 2018 and shortly joined staff as the new systems administrator and second in command of IT. For the IT team, that was a very transitional year, with the existing staff leaving and handing over to us newcomers everything that they had built. The old systems were a mixture of appliances and frameworks and languages and some strange disparate microservices. The ticketing system alone was 4 or 5 different services, some written in Ruby and others in Go. It was designed many years earlier for different requirements and constraints, for a very different environment than what we now faced, and where we wanted to go with the IT systems. For example, it was designed to run ticket redemption at the convention center, that's the bit where you scan everyone in, completely offline. But this meant we would never be able to do online ticket sales during the event, and it made it very hard to try and set up mobile handheld scanners that would work outside over 4G or LTE. Among the many changes we made was, with the blessing of the old guard, building a brand new ticketing system. Now, we couldn't find any existing open source or low-cost solution that would do what we needed, so again, we wrote our own from scratch. Smash is entirely driven by volunteers, so we needed a stack that volunteers would be able to get the hang of quickly, so we chose a JavaScript TypeScript stack. We used React.js for the front end, Node.js and Express.js for the back end, and MySQL for data persistence, since we already had MySQL infrastructure for our WordPress sites, including things like automatic backups, and I didn't want to have to manage 2 database stacks. To host the sites, we decided to use Kubernetes, mostly because I wanted to learn Kubernetes, but also because it made a bunch of things really easy, words that may never be said again as it's gotten more complex, such as pushing out updates to the software, managing secrets, automatically managing Nginx and Let's Encrypt certificates, and it let us establish a really solid infrastructure as code foundation. And in the long run, it has been a lot easier than manually configuring a handful of VPS boxes. So this is our rough architecture for the ticketing system. Requests to /API go to the Node.js backend, which talks to the MySQL instance, which is then backed by a persistent disk. All other requests go to a tiny Nginx container that serves up the static frontend. If we add in the WordPress site and then account for replicas, this is basically what our setup looked like at the time. And this setup served us nicely through 2019. In fact, we built the system all through 2019 in a very just-in-time approach. You might even call it agile. But for example, when we launched ticket sales that first year, we hadn't finished the code to generate PDFs for tickets or receipts. So we later had to backfill all those orders by generating those PDFs and sending out their emails once the code was ready. Another example is the ticket redemption code, which was only finalized and deployed to production the night before exhibitor setup day, when we had to scan in all the exhibitors. But it worked, and it held, and we ran a convention that weekend, including a concert with almost no technical issues. Throughout 2020 and early 2021, we built some new features, refactored the code, updated NPM packages, and had our very short-lived 2020 ticket sales. But there were no major changes from the 2019 codebase or architecture. So how come, in 2021, this system fell flat on its face? There are many different models that you can use to analyze risk and accidents. And the Swiss cheese model is used in the aviation industry, and it's one of my favorites because it is so often accurate. The model works roughly like this. For any event that you don't want to happen, there are a bunch of different barriers that contribute towards protection. Each of them are ultimately fallible, but in different ways. For that event to then occur, multiple barriers have to be individually breached. If any single one of these barriers holds up, then the event, usually some kind of accident or disaster, is still prevented. The more barriers that were breached, the closer you've come to total disaster. Over at the Snake Oil Academy track, they would probably call this defense in depth. But here we're not trying to fend off an attacker. We're just trying to protect ourselves from failure. For a worked example, let's look briefly at US Airways Flight 1549, the infamous Hudson River ditching. Big content warning on this one. If you're not comfortable, come back in about 2 minutes. For the rest of you, I'm going to assume that by now you've heard about what happened, because it's pretty famous at this point, and that whole series of events really should not have occurred. For a start, the aircraft encountered birds, technically geese, on takeoff. Engines are designed to withstand ingesting birds. In fact, during testing, they fire frozen birds at engines from a cannon. According to the official NTSB investigation report, though, if a bird enters the engine near the outer edges, it'll most likely strike only the fan blades, continue along the bypass duct, and get ejected out the back, probably dead, possibly cooked. But because it hit the inner part of the engine, it got ingested into the core. Even then, a twin-engine aircraft like that can still fly, including a full takeoff, with only one working engine. We have some basic redundancy, that's great. But unfortunately in this case, birds took out both engines. Even then, an aircraft can still glide for quite some time. Though if you ask a pilot, they'll probably call it falling slowly rather than gliding. Regardless, they hadn't gotten high enough yet. I didn't have very far to glide, definitely not far enough to a runway. And so on and so forth. Different layers of protection, redundancy, or resiliency, each one breached until they had no choice but to crash into the Hudson River. Fortunately, in this case, there were still layers of protection that held up. The pilots used their training to ditch the aircraft without crashing it and destroying it. The flight crew evacuated everyone before the plane sank. And the planes were equipped with life rafts, so people actually had somewhere to go. In this case, it wasn't a total disaster, and a good amount of those cheese layers still held up. But in the days that followed the 2nd of May, 2021, I was strongly reminded of this model as we worked through different problems in our ticketing system, none of which alone could be pinpointed as the singular cause of our failed ticketing sales launch, but all whom could have helped prevent or mitigate it. The first issue that we managed to identify and fix was that the main WordPress site went down. It shared a database server with a ticketing system, and whilst we hadn't had a single problem with it in previous years, even on the day of convention with people hammering the schedule, all we could see was the generic error message, error establishing a database connection. I suspected this was due to a mixture of increased load on the main site and on the ticketing side at the same time. I went digging and quickly discovered that the default connection limit in MySQL is 151 concurrent connections. I have no idea why they picked that number. Perhaps whoever came up with it is a fan of the original Pokemon games. In any event, we increased the connection limit to 500 and that particular problem went away. Unfortunately, we were still seeing errors on the ticketing system. The most common one we saw in server logs was a connects timeout error. Timeout acquiring a connection, the pool is probably full. Are you missing a .transacting call? The way that most database client software works is that they don't create a new SQL connection every time they need one. These get pooled. When you request one, you either take one from the pool or get handed back a brand new one. That's up to the pool to decide. And when you're done, you hand it back to the pool, and it either scrubs it for reuse later or drops it entirely. Again, that's up to the pool to decide. In this case, I believe the error message is technically wrong, and it means the pool is probably empty. That is, all the connections that it has have already been handed out, and it's not going to create another new one for you. The first thing we did was go looking for any places in the code where we were requesting a connection, but not handing it back. And we found exactly 0 instances of that. The code was doing the right thing. So the next question is, how big is this pool exactly? We did some initial digging and found buried away in the documentation that according to the default settings, the pool has a minimum of 2 connections available and a maximum of 10. We had 2 servers and hundreds of users, so we likely needed far more than 20 concurrent connections. We increased the connection pool limits, deployed it to production, and still no improvement. At this point, we decided to push the panic button and put the site into maintenance mode. This is a special mode where users can't really do anything, and it's designed for shutting down the site to perform maintenance such as moving between servers, rebuilding the cluster, or some kind of urgent database operation. In our case, we just wanted to pull the plug so that we could start seeing what actually happened. Unfortunately, the site was under such heavy load that we couldn't even get into the admin settings and save our changes. I manually flipped the switch in the database table, only to then discover that the website couldn't even load the settings value due to the site crawling so slowly. We ended up going into the code base and changing the client side is maintenance mode function to simply return true and deployed that straight to production. So by now we should have no users and be able to begin a thorough investigation. But strangely, this is when orders kept coming into the system. These were hitting the payment processor and our emailing provider. And now that we had no new users coming through the system, we were actually somehow selling tickets. The system was slowly working through a backlog. I suspected this was a backlog of users who had already started the ticket flow, or they were spamming the refresh button towards the end. At that point, the is maintenance mode function is no longer checked. But as these orders started coming through, we started getting complaints through customer service that some customers had been double charged. We spent some time looking through the orders and cross-referencing them with the payment provider and discovered 2 surprising things. One is some customers had indeed been double charged for their order, as they must have been submitting the order form multiple times and retrying on error. We refunded these extra orders and we cancelled the duplicate tickets. We hypothesized based on screenshots we'd been sent that what must have happened is customers submitted their order, which took so long that the Nginx Ingress controller, which was running on basically default settings, gave up after 60 seconds and returned an HTTP 504 gateway timeout error. But Node.js and Express.js continued handling the requests and ultimately fulfilled the order. The user never saw that. So when they saw the 504 error, they simply resubmitted the order, not realizing that they were now submitting a second order, or a third. Or for that one person, number 12. To fix this, we increased the proxy read timeout value to a larger value than the actual application server would take, so that the application would timeout or fail before Nginx gave up on the request. That should also help to reduce our load, because if each user is making multiple requests, then our effective user count, and therefore our load, is significantly larger. It's multiple times what it should be. But even more strangely, surprising thing number 2 was that some customers experienced the exact opposite case. They'd been charged for their order, but they had no corresponding ticket in our system. There is logically no way this should be able to happen, as the way the code was structured is we create a payment record, then we call out to the payment processor's API, and then we update the payment record with the result of the API calls. There should be a payment record there at all times. We went digging through the code and discovered a horrible mistake. The code that created the payment record and the code that called out to the payment processing API were both in the same database transaction. If the container gets shut down in the middle, for example, when a new image is deployed, then the payment record doesn't actually get saved to the database. This could also explain our problem overall. If the payment processor takes a significant amount of time, then we hold our transactions open and exhaust the connection pool. That's it. There's our smoking gun. Everyone can go home. Clearly not. There's still 15 minutes left in this talk. Since we no longer had any real customers online at this point, we pushed the fix to staging and ran a synthetic load test, talking to the payment processor's testing API to ensure that we don't spend or take any real money. Waiting with bated breath, we ran our test script, and it still failed spectacularly. Whilst this was clearly a problem, it couldn't be the problem. So at this point, we were pretty much lost. We knew that we had a problem. We knew that it was likely related to the SQL database, since we had WordPress and Connects both complaining about SQL connections, and we knew that it was induced by a massive load of customers trying to buy tickets. But we had no clue what was really wrong. As far as diagnosing and optimizing SQL goes, this is something that I've seen before many times at work. And when I get stuck, we have some very good DBAs that I can always turn to for help. But I didn't have that here. And I couldn't even turn to my usual tools that I use at work. At work, we rely on Microsoft SQL Server, and the best tool by far for initial investigation is a Microsoft SQL Profiler. This is a wonderful tool that can show you live every SQL command being executed, who ran them, how long they took, what machine it came from, so on and so forth. Normally I would look here for long-running queries or blocked queries and start to unravel the mess, but I actually could not find any equivalent tooling for MySQL. The only option left was to instrument the application itself. Fortunately, and well, what got us into this mess is this is our own application and not a third-party proprietary one, so we could do this fairly easily. We did two things here. One is we added a warning if a transaction takes too long, an arbitrary amount of time to run. And two is we ran the application in development mode with an environment variable set so that the ORM would print out every SQL query it ran as it ran it. We ran a few test orders in development, we sat down, looked through these queries, and we noticed a few interesting things. Firstly, each HTTP request to order some tickets had about 5 or 6 transactions running. This highly increases the chance of failure when the connection pool is exhausted. Once a request gets that first connection, there is no guarantee that the connection pool will give it the second one it needs, or the third, or the fourth, and so on. We consolidated some of these transactions together and managed to bring it down to 3. Secondly, we noticed a lot of extra queries that we didn't need. Often when we created or updated a row, the ORM would subsequently select that row again, but we never did anything with the new result. We changed a few method calls and those select queries disappeared. Thirdly, we noticed a few of them were select for update, which locks the row. This was by design, as we keep track of how many sales each item or bundle has. Definitions: an item is an individual thing, such as a Sunday pass. A bundle is a collection of items, such as a weekend ticket, which would contain both a Saturday pass and a Sunday pass. This is so we can limit certain purchases. For example, our discounted early bird bundle was limited to the first 500 people. And in 2019, when we held the Anisong concert, the hall only has a certain number of seats. We can't oversell that, or some people would have nowhere to sit. This year we also have things like, square meter per person capacity limits to worry about, but we haven't programmed any of that into the system. The row locking is only supposed to be very brief. We lock the rows only for a very small period when we create the pending order and increment the counts for the relevant items. If the order processing fails, we lock again briefly and decrement the counts. We don't keep it locked for a long time, but if we did, this would also explain a large amount of the performance problems. With the row locked during an order, somebody loading the homepage can't even load the list of things available for sale, as we can't determine if something is out of stock or not while it's locked. Technically, we don't even know if it exists, since the definition of the item and the quantity are stored in the same table in the same row. Since we don't have hard limits this year, we checked with the executive team to see if we need to stick to the hard limit spec we had in 2019, or if we can disable the row locks and maybe just go over a little bit. They gave us the go-ahead, we disabled the row locking, we ran the test script again, and this time it actually helped a little bit. But each request was still far too slow, and after a minute everything started timing out again. Now, at this time, while the team was digging through SQL, I decided to look at a different problem. Something we noticed while rebooting containers and deploying new ones during the ticket launch was that the server-side container image was taking about 3 to 5 minutes from the time that the container started until the time that it started listening for HTTP requests on the TCP port. I roped in a JavaScript expert from work to give me the rundown on how to do some basic performance analysis and debugging with Node.js, and he showed me how to connect the Chrome developer tools to a Node.js application. From there, I extrapolated a bit, and by exposing the correct port number through Docker, I managed to attach the Chrome dev tools to Node.js inside the Docker image. Strangely, while stepping through it on my MacBook, the performance problem just seemed to be in importing types. So I did some chin scratching, I did some thinking, I did a lot of Googling, and discovered there's an open issue on GitHub that Docker for Mac is just apparently really, really slow at file system operations. And clearly that's not our production problem, as Azure Kubernetes does not run on Mac OS. So the next steps I took to debug this was to create a new Linux virtual machine. I used Ubuntu because it's an ancient African word for slightly easier than Debian. I installed that on my Windows workstation PC, installed Docker in there, and started to debug from there. When running Docker on Linux, our container started up pretty much instantly, and it listened on port 3000 immediately. No performance problem to be seen whatsoever. But one of the main selling points for containerization is that you have perfect reproducibility, as you have the same container image on all your systems. The only thing that's different is hardware performance characteristics, the network, and the underlying Linux kernel. And I didn't think any of those were relevant here. So I went digging through our Kubernetes YAML for any major differences and came across this fun block that I'd written a long time ago and mostly forgotten. Back after the 2019 convention, while we were downscaling everything back to minimal business-as-usual operations, the YAML linter in Visual Studio Code suggested to add resource limits, and after reading through the docs, I thought, well, that sounds like a really, really good idea. Resource limits sound good. So I added some limits based on the peak usage we had observed during the convention that year. I recreated the container image on my Ubuntu VM, but this time limited the CPU to just a quarter of a CPU core, and would you believe it? The image took 3 minutes to start up. This immediately threw a new light on the whole situation. Was it possible that our SQL, after all, was perfectly fine, but we were just CPU constrained? After all, during the 2019 ticket sales, we hadn't written the PDF generation code, and the 2020 ticket sales were quite lackluster due to the looming pandemic and just general uncertainty. We commented out the function call to generate the ticket PDF and attach it to the email. We pushed a new code to staging only, we reran the load test script, and bang! All our requests were handled lightning fast, no performance problems whatsoever. Unfortunately, we can't actually ship these changes as people need their ticket PDFs if they're going to attend the convention. That's the whole point of buying the ticket. Increasing the amount of CPU allocated to the container as well isn't hugely beneficial. We can go from 25% up to 100% and handle maybe 4 times as many requests if it scales linearly, but any more than a single vCPU core won't help, as Node.js is famously single-threaded. It's not going to farm out different incoming requests to different CPU cores by itself. In fact, if you Google, how do I make Node.js use more CPU, the top Stack Overflow answer is run multiple copies of it, duh. So we would somehow need to offload the PDF generation another way. Now that we figured out the technical side, we still have the human side to understand. Why did we have so many users trying to buy tickets? We had never seen this level of demand before. I don't know for certain, but I have 2 hypotheses. The first is due to COVID. In 2020, there were almost no events due to the pandemic and the lockdowns. There was no Smash, no Supernova, no Oz Comic Con, and no PAX Australia. It's quite possible that people were just hungry for their cultural events after a year of deprivation. The second hypothesis is due to marketing. Our early bird special was limited to 500 tickets, but it seems that at least a few people misinterpreted the social media posts and thought that there were only 500 tickets to the event in total. Some critical thinking might suggest that downscaling the event that much isn't really financially feasible, but you can just get up early and smash the F5 button and be one of those lucky people. So now, with all that information gleaned from our investigation and the fixes we put into place, we can now explain the original events on the 2nd of May in its entirety. Due to a huge amount of demand after a year of cancelled events, and possibly fed by marketing miscommunication, we had way more users try and order tickets than in previous years. As the first orders started coming through, they held open SQL transactions, which prevented subsequent requests or request continuations from obtaining the connection they needed. When we restarted and deployed new backend images, this interrupted a couple requests inside the dodgy payments transaction, so their payment was never recorded. PDF generation used up the full CPU allocation, so incoming requests were added to the backlog. The server did not have enough CPU to process this, and definitely not its 25% CPU, with 3 out of 4 hands tied behind its back. And so, after 60 seconds, Nginx gave up on the request, but Node.js continued to process it. When users got gateway timeout errors, they retried, which only further added to the backlog. And after a certain point, new requests would always time out before they could be handled by Node.js, since the backlog was so large. None of these alone can be pinpointed as the cause of the outage, but our cheese had some pretty big holes. This all went down on Sunday, and the investigation ran for several more days. But we needed to have ticket sales operational again by Thursday. For Thursday, we made several key changes to do our best to avoid a repeat of the crash. On the application side, we had fixed the open transactions and consolidated a few more requests into fewer transactions. We removed SQL queries from the code that we didn't need, and we disabled the row locking. We also increased the connection pool size. We also plan to offload PDF generation to some Azure functions. For you AWS folk, think Lambdas, but obviously we wouldn't have that ready by Thursday. On the operations side, we had increased the MySQL connection limit. We had increased the CPU limits for the server containers from 25% of a CPU core to 95% of a CPU core. And we added an additional server for a total of almost 6 times as much CPU capacity as previously. The last change we made was to human factors. Instead of hyping everyone up again for Rush Unlimited ticket sales, we changed the terms. So anyone could purchase a discounted weekend ticket across a 10-hour window from 2 p.m. until midnight. And then we opened that window a few minutes early to deal with any overeager customers. Thursday's ticket sales were an absolute success. Not only did we manage our pre-sales without crashing again, we set a new internal record for the number of pre-sales tickets sold in a single day. Unfortunately, due to the Delta outbreak across New South Wales and Australia, we had to postpone the event 4 weeks ago through to 2022. However, the lessons we learned here are quite valuable, and I share them with you all today in the hope that they won't be repeated frequently. The key things I took away from this were to load test regularly. If you don't think you need a load test for the event, do it again anyway, and make sure the test is harder than you think you'll encounter in production. You also need to understand profiling tools before you urgently need them. We need to make sure to correctly deal with timeouts and request cancellation, something that very often goes overlooked in application development. To make sure that any panic buttons are actually disaster-proof and will work in an emergency. And mostly, not to perform any CPU-intensive work in a single threaded web application. That's literally just asking for trouble. Thank you.
Thanks, Yaakov. That was an excellent talk. And yes, lots of great lessons there about how to respond to various kinds of oops. So I'm sure that everyone enjoyed that talk. I've seen a lot of really positive comments there in the chat. Now, I don't see any other questions, but if you would like to hang out, I know you've been in the chat already, Yaakov. So if people do have questions and want to ask you about anything about this, what you've learned about how to instrument MySQL, if you've actually, I have a question. Have you managed to find any profiling tools for MySQL that would be useful?
I still haven't. If anybody knows of something that does what we need there, I would absolutely love to know. Please drop me a tweet or an email.
That is
elephant.
Mind-boggling. I recall having to do this with other database systems many, many years ago when I was technical, and yeah, not having that would be horrendous. Thank you, Yaakov, once again for giving a great talk. And for everyone else, we're going to take a bit of a break, and we will be back in a few minutes, about 15 minutes from now. Let's see, we're scheduled to be about 11 o'clock. So you've got 15 minutes before our next talk with Amit Sahar, which is called Planning for Failure Using Chaos Engineering. So we've just had a talk on how to fix things that got broken by accident. Now we're going to break them on purpose. Yay! We'll see you all back here in about 15 minutes.